everyone, my name is Savine and I'm a PhD student in CEM department at Columbia University. I'm going to present part of our recent effort toward optimizing ambulances transport in New York City. Ambulances transport is usually on the basis of transferring the patients to the closest appropriate hospitals. To choose the closest hospitals, we need to have an accurate estimate of ambulance routing travel times, which can be inferred from historical data. With estimated travel times, we can build hospital suggestion pattern, which is central to the EMS ambulance dispatching system. We use two sets of data. The first data set is the shortest past travel times generated by network analysis model for every Adam to hospital pair. The second data set is the historical ambulance routing travel times. The latter data set is available for a limited range of Adam to hospital pairs, mostly shorter trips. For example, here in this histogram, we show the number of transports from a given Adam, highlighted here with blue color, to different hospitals. And as you see, the number of trips is becoming less and less as we go down in the list of sorted hospitals, or the size of red marker here, which is proportional to the data count, becomes smaller as we go further. On the other hand, the network analysis travel times are representative of city vehicle driving behavior and not ambulance behavior. Depends on the severity of incident. Ambulances can navigate with lights and sirens on, and they can also skip the traffic lights. So basically, we need to calibrate the network analysis travel times to match with ambulance behavior. To do so, we construct a linear model between network and ambulance average travel times, and using Gaussian process regression, we calibrate the network analysis travel times. In the next step, to create the pattern, we use a probabilistic decision rule to determine closer hospital. Basically, we rank the hospitals based on to which more patients will arrive faster. But for some cases, like here, it is not easy to say which hospital is closer. And especially when probability is closer to 0.5, we call it close calls. You can see these close calls at this map here. These calls can happen for atoms located in between different hospitals, shown by red-blue color here. So making decisions in this situation is really hard. To tackle this problem, we use Bayesian bootstrapping to calculate the confidence level by calculating the number of times, for example, hospital I is closer than hospital J across different samples from the ambulance data. Finally, we rank hospitals based on calibrated network analysis travel times and then adjust it with ambulance data with high level of confidence. So here in this figure, we see that in all samples, hospital 1 is closer than hospital 2. We are 100% sure that hospital 1 is closer, but this is not the case for comparing hospital 13 and 18. And finally, our constructed pattern was implemented in FDNY's CAD system and improved ambulances travel times in New York City. And I acknowledge the help from FDNY team and the support from Google and the Tides Foundation and the Columbia Urban Technology Pilot Award. Thanks for listening.